All right, guys. Today is Friday the 30th, so we're getting very close to Halloween. I'm going to go through our practice. This is going to be a kinetics practice. This will be essentially the end of this chapter. There may be one other thing that we can talk about when we hit kinetics again. So we'll hit kinetics again right before the AP test. We'll review everything, and so we'll hit some other stuff then. But we're going to go through integrated rate laws and some free response practice. All right, so I'm just going to answer the questions here. So number one, briefly describe when an integrated rate law is needed. And basically, anytime we're not using initial rates or when we need to determine the concentration at a given time. And that time can't be time zero. So at any other time, if we want to find the rate, we need an integrated rate law. All right, if a reaction is zero order, a graph of the what versus time will produce a straight line. And that's concentration. So if it's a zero order graph, when we graph concentration versus time, we will get a straight line graph, and it'll look like this. It'll have a negative slope. All right. How can K be determined? Find the slope of this. The absolute value of the slope is equal to K. And that's because K can't be negative. All right, so graph of concentration versus, wait, where am I? There, if the reaction is zero order, how can K be determined? Slope. Graph it and then find the slope. The equation for slope, again, is y2 minus y1 over x2 minus x1. Take 2 points. Remember, it's x comma y. Take 2 points and plug them into this equation. Do the rise over run. Okay. If a reaction is first order, then the graph of the natural log of the concentration will give us a straight line. So here's our first. So this was zero order up here. For first order, we're going to do the natural log. Oh, and I don't have enough room to write here. So natural log of the concentration. So I wrote Ln and then brackets. I know it's hard to see. And this is time on the x-axis. Again, we're going to get a negatively sloped graph. It's going to look just like the first one. And the slope, again, will be the absolute value of the slope will give us K. All right. And let me rewrite this in black because I want everything in the same color. Slope. All right. If the reaction is first order, how can K be determined? Slope. So absolute value of the slope. Okay. So that was 1, 2, 3, 4, and 5. Okay. I'm going to have to erase. And then I'm going to have to scroll down. Okay, so number 6. If a reaction is second order, a graph of 1 over the concentration. Let's say your reactant's A is going to be concentration of A. So 1 over, or A to the minus 1, like we like to put it sometimes, that will produce a linear line, a linear graph. So if we graph it 1 over the concentration over time. And this time we're going to get a positively sloping line. So then the slope, not the absolute value of the slope, but the slope as itself is equal to K. All All right. So again, y2 minus y1 over x2 minus x1. Now, why are these three important? The importance here is because, remember, initial rates change. So here's concentration versus time. So if I make a graph of the concentration versus time for any reaction, if I just do concentration versus time for any first or second order reaction, that means that as the reaction proceeds, the concentration decreases because and the rate will decrease because I'm losing reactant. And so here's our curve. Okay. Actually, let's see, that would be decreasing. Is that the right curve? Let me look over here and see. What would our curve look like? Oh, okay. A curve would be like this. That's increasing. That's 1 over. Oh, okay. I got it. Just took me a minute. Our curve's going to look like this. There we go. All right. So since the concentration versus time graph for our rate is curved, we can't use it. You would need calculus to determine it. You would need to take the integral of this function in order to get the area underneath that curve. All right, so when we integrate it, we end up with an integrated rate law. And for a first order, we're going to need, so zero order, we can say, okay, concentration versus time graph will give you a straight line. For a first order, you're going to need the natural log of the concentration over time. So that's y-axis is the natural log of concentration, x-axis is time. And then for the second order, one that we're doing right now, the only way you're going to get a straight line that we can analyze is if you do the reciprocal of the concentration, or a minus 1. So 1 over the concentration. And there are some cute ways to remember this. So if you want to remember that the first order reaction integrated rate law requires the natural log of the concentration to be true, for that to be a straight line. Just remember that it's always natural to want to be first. It's always natural to want to be first. And remember, it's the natural log. And so the first order is the natural log. It's always natural to want to be first. Then there's a cute little thing for the second law, and that's that do you want to be second? That's upside down thinking. So if you want second order, upside down thinking, put the concentration in the denominator. Just some kind of little tricks that might help. All right, so number 8, the absolute value of the slope of the graph, regardless of the order of the reaction, is used. This is because the K is never negative. K must be positive. All right, if the integrated rate law is used, the reaction is, so we can look at this rate law and notice that it's just concentration in there. It's not natural log, and it's not the reciprocal. And so this must be 0 order. Okay, so that is our equation for our 0 order rate law. And notice that it has the form y equals mx plus b, where y is equal to, and let me erase so that I can do this. So y equals mx plus b, where this is y, the concentration of your reactant, the slope is k, x is time, that's the variable that we're manipulating. We're trying to see how the concentration changed versus time. And then the y-intercept is the initial concentration. So y equals concentration of A, x equals, or I'm sorry, m, the slope, m is equal to negative k, or the negative slope is equal to k. And then x is our variable that we're changing, which is time. We're seeing how the concentration changes with the time. So y is A, the concentration of our reactant, x is time. That's what we're comparing it to. And then B, the y-intercept, is the initial concentration, which is what that means. That means the initial concentration of A, or whatever your reactant is. So this is a zero order rate law. No natural logarithms, no inverses, okay? And the reason for that is because the straight line occurs when you get, when you graph concentration versus time for a zero order. Remember, zero order rate laws have this rate law. Rate is equal to K. That's it. It does not depend on concentration. So so the rate constant K determines everything for these reactions. The concentration, you can double it, you can triple it. The rate ain't changing. The rate depends on temperature. And so the rate depends on K. That's it. So that's the zero order. Another cute thing to remember here for integrated rate laws is CLR. For the first order, you need concentration versus time, right? For the second, oh, I'm sorry, that's zero order. I keep saying first because it's the first one, but it's the first one that we're doing is the zero order. Zero order. So that'll be concentration versus time. We'll get that. Then first order is L. So that's the natural log of the concentration versus time. And you'll get that negative line again. And then the second order is this. So I just remember CLR. CLR. C is concentration. L is natural log. And so the graph is natural log versus time. And then R is reciprocal. 1 over the concentration of A. If you graph 1 over the concentration versus time, then you get a positively sloped line. And then you can also keep that to remember which one is which. So zero order, you're going to just see the concentration of A. First order, you're going to see the natural log of A, whether it be the graph or the equation. The graph is the equation in graphical form, right? It's showing you the function in graphical form. And then the second order is 1 over concentration of A, or A raised to the power of -1. Remember, when you raise something to the power of -1, it goes in the denominator. Okay. So that is number 6, number 7, number 8, number 9. That's zero order. Okay, so we've done all these. Number 10. All right, if this is our integrated rate law, what is the order of the reaction? And this means the overall order of the reaction. Okay, not the order with respect to one reactant, but the the overall order. Okay, and so since this is the natural log, remember it's CLR. Since it's natural log, it's first order. This one was 0. This one was second. Okay. Okay, if the integrated rate law is used, the reaction is second order, because this is 1 over the concentration, right? Reciprocal is the second order. Okay, now we're getting to the other problems. Let me think about where I got this one. This one's from the NMSI notes. So let me pull my NMSI notes. I don't know why I put them up. I thought I was done with them for the day. Oh, where are you, NMSI notes? Oh, they're right in front of me. Here we go. Okay, so let's look for half-life stuff. All right, Mr. Half-Life, where are you? Integrated rate law. Here's half-life stuff. Okay. Okay, here we go. So I'm going to do number 12. Okay. I'm going to need some room though. So let's do this. Let's take this. New. Do this. Here we go. Okay. Can I get more room there? No, I can't. Okay. That's good. All right. A certain first order reaction has a half-life of 20 minutes. Most nuclear decay is where like the atom is breaking down and it's splitting and you're calculating the half-life. So if you had a radioactive isotope, you started with 100% and then half of it breaks down. So now you're at 50-50. And then it breaks down again right? So this is where it's all half of it's gone, and then a fourth of it's gone, and then it's 25 to 75, and then it's 1/8, which is 12.5 to 87.5, and so on. So that's after 1 half-lives, 2 half-lives, 3 half-lives. So that's how half-life works. It's the time it takes for half of a sample to decompose, or the time it takes for the reactant to get to half of its concentration. Half of the concentration is used up. Okay, so we want to calculate the rate constant for this reaction. So for any half-life kind of problem, we're going to use this equation. And this equation comes from the first order integrated rate law. All right, and they showed you how they got that equation in the NMSI notes. How you get from one equation to the other one doesn't matter, but you just want to know which equation to use. So we're going to use half-life is equal to 0.693 over K. And this 693 is the natural log of 2. That's what that is, okay? So type in natural log in your calculator, hit 2, you get 0.693. So we're going to plug this in. If you want to solve for K, these two could just switch. And essentially, I can multiply by K by both sides and then divide by T 1/2. So let me show you how I would do that algebraically. T 1/2 equals 0.693 over K. If I multiply both sides by K, let's see what I get. Those K's cancel. Now I have K times T 1/2. And that's all one variable, T 1/2. It's all one variable. And that's equal to 0.693. So then I divide by K to both sides. And now I can see I got that. Wait. Not divide by K, divide by T 1/2 to get K by itself. So now we can see that K is equal to 0.693 divided by 1/2. So let's write that. K is equal to, and this is baby K, so however you wanted to denote that, 0.693 over T 1/2, 0.693, and the time, the half-life is 20 minutes. Tells you right here the half-life is 20 minutes. T 1/2 is 20, so just divide that by 20. And we get 0.03456. And our unit will be the rate constant. What is our unit here? The rate constant. Natural log of 2 on top. So T 1/2 minutes. Minutes. There we go. I don't know why that took me so long to figure out. That many minutes. Or you can convert it to seconds if you wanted to. All right. Yeah, because this is minutes here. Yeah, so it's not sure what the unit is. I'll have to think about that. This one's in the NMSI notes, so if you guys look in the NMSI notes, you'll see what the units are. It may be minutes minus 1. That may be what it is. Okay, let's do B. This is going to take a while. We got lots of problems, but I'm going as fast as I can. So how much time is required for the reaction to be at 70% complete? All right, so think about it. I have an initial concentration of my reactant. At the beginning, I have 100% of my reactant. After 1 half-life, I'm going to cut it in half. That's 50%. Okay? After another half-life, I'm going to cut it in half. So this is my first half-life. The time it takes for my concentration to cut in half. And then I got 50%, so that's 50-50. And then I'm going to have a second half-life. And here I'm going to have 25%. 25% remaining. That's the same thing as 75% complete. So 25% is what's here. Look at the other three. What is that? That's 3/4. 75%. So how many half-lives? 2 half-lives. 2 half-lives. I can't help but think of the game Half-Life when I do this. I don't know if you played that game, but that's an old shooter game from the 90s on the computer. My son likes it. 2 half-lives. And so each half-life is 20 minutes. 2 half-lives, 20 times 2. It'll take 40 minutes. Don't overthink these problems. They are tricky. And I remember when I first did this, it was difficult. But think about folding the paper. I mean, if you have to, take a piece of paper on the AP test, fold it in half. Let me show you guys how to do that. So, yeah, let's do this because I wanted to show you guys this too. I showed it in the video, but I didn't explain it. So I'll take my paper. It's 100% white. So this is 100% of my reactant, whatever it is, okay? After 1 half-life, I'm gonna cut it in half. So I'm gonna fold it in half. And if you need to do this, because this doesn't make sense until I did this. So now I have my paper folded in half. And now what I'm gonna do is I'm gonna say half of my paper is now gone. I've lost my reactant because the reactant is proceeding and I'm making my products. So this has already turned into my products. So if you're talking about a chemical reaction, we're saying that half of it has been used up. If you're talking about a nuclear reaction where an atom is splitting and it's making a daughter product in a nuclear process, half of it has been decomposed. Half of the atom, half of the mass has been split in half. And so these problems can relate to kinetics of a chemical reaction or with nuclear reactions where an atom is splitting. All right, so now that's 1 half-life, 50-50. Now let's take it again. I'm going to close it up. And it's important that you close it up. And I'm going to fold it in half again. So now it's in fourths. I'm going to open it back up. I got that. And so now I'm going to take what I have left and say, okay, let's make another half-life. Let's cut it in half. And you know the funny thing about this, guys? This activity is like an epiphany from when I did it. A student. This is a student's idea. I got this from one of my students. Brilliant. So this is 3/4 used up, 3/4 decomposed, and 1/4 remaining. Okay, fold it again. Close it. Fold it in half. And I'm hoping this is helping with the concept of half-life. So now we've done 2 half-lives. We have 75 gone, 25 left. So now let's do 1 more half-life. Cut the remaining concentration in half again. Okay. Now I have 1/8. And I can see that 1/8 remains and 7/8 is gone. Cut it again. You got to fold it all the way back to the 1/8 and then cut it in half again. And this makes me think about that thing that I learned in like elementary school or middle school where they say that if you were to fold a piece of paper in half, like, I don't know, 50 times or however many times you can fold it, if you could fold it, let's say 100 times, then it would be as thick and it would be really thick and you'd be able to get to the moon. That doesn't make sense to me, but it makes me think of that when I fold paper like this and fold it over and over again. So if I take what's left, the 1/8, I'm gonna cut it into a half, which will be a 16th. So let's cut that in half. And now you can see that I got 1/16 left, and we can keep going. And that's how half-life works. It's the time it takes for half of the sample to be decomposed or altered or broken down if it's nuclear, or half the time it takes for your reactants to be used up. Okay. Okay, and that's it. Let's go back, okay. All right, here's another question. The rate constant for the first order transformation of cyclopropane is 5.4 times 10 to the minus 2 hours, or per hour. Calculate the half-life, okay? How do we do this one? Half-life is equal to 0.693, or the natural log of 2. Divide that by k. 0.693 divided by 5.4 times 10 to the minus 2 hours minus 1. We get 12.8 hours. Okay, so our half-life is 12.8 hours. That's how you calculate it. You can calculate half-life, you can calculate K. Either one from this equation. What fraction remains after 18 hours? Okay, our half-life is 12.8 hours. Okay. Wait, 18 hours? No. This should not be 18. Let me fix this. This should be 51.2 hours. 51.2. So what fraction remains after 51.2 hours? So our half-life is 12.8 hours. So what fraction remains after 51.2 hours? Well, let's divide 51.2 by 18. What do we get? Not by 18, by 12.4. Where did I get this 18? I'm going to take the 51.2 divided by 12.8. 51.2 divided by 12.8. There we go, 4. 4 half-lives. So what fraction remains after 4 half-lives? All right, so we start with 1 whole. After 1 half-life, we have a half. After 2 half-lives, we have a fourth. After 3 half-lives, we have an eighth. After 4 half-lives, we have 1/16. So just type, you can write 1/16 as an answer, or you can write it as a decimal, 1/16. Either of those is okay. That's the fraction. 1/16 would remain. And so you just divide this over and over again. This is our first half-life. That's our second. This one all the way back here is our third. That's our fourth. Awesome. And those are easy. All right. A balanced equation for this reaction is 2NO plus F2 makes 2NO, 2F. Here's our rate law. So they're giving us the rate law. This is the experimental rate law that they're giving us. So this one is correct. This is a suggested mechanism for this reaction. Remember that you can write a rate law from elementary steps. These are called elementary steps because it's a mechanism. Each step in a mechanism is called an elementary step. And you can write a rate law from them. So I could write the rate law for this one. I could say the rate is equal to K times NO2 times F2. And that rate law says that the order of NO2 is 1, and the order of F2 is 1. And the overall order for that step, the slow step, is 2. Okay? And then we can write a rate law for the next one if we wanted to. F times, so K times F times NO2. Now, F is an intermediate. So we can't actually write a rate law in terms of an intermediate because if you look at our reaction up here, it doesn't exist until after the first elementary step. And so we really can't write a rate law for the second one. But it's a fast step, and we're going to ignore the fast step anyway. We only care about the slow step. The slow step, the rate determining step, will determine the rate, and therefore it will determine the rate law. So notice that the rate law that we wrote for the slow step right here is equal to the rate law that they told us. So yes, it's an acceptable mechanism because the rate determining step matches the slow step. Okay? And you guys should practice writing these answers. I'm not going to write some of these answers because it'll take a while, but you guys can pause the video and write the rate law from the rate determining step, from the rate determining elementary step. Rate determining elementary step. So the rate law from the rate determining elementary step matches the rate law that is given, which was determined experimentally with our tables. Okay, what about the stoichiometry? Let's take this reaction and check it for stoichiometry. We need to add these two together and see if we will get our overall reaction. So this is our target, and this is what we're going to have. So notice that the fluorine will cancel with itself. We call that an intermediate. It is produced in the first step and then consumed in the second step. It's not in the overall reaction. Notice up here, there's no F by itself. Okay, and the reason for that is F by itself is extremely reactive. It always occurs in pairs, just like our other diatomic gases. All right, so that's an intermediate. So let's add these up. NO2 plus NO2, that's 2 NO2. Plus F2 makes N2 NO2F. 2 NO2F. Notice we get the same thing we got there. Okay, so the stoichiometry works out. So two ways to tell. Does the slow rate determining step make the same rate law? If so, that's the slowest step, and it's compatible with the mechanism. So the mechanism is compatible with this reaction. It's a possible mechanism for this reaction. And then the stoichiometry lines up too. Let's do one more thing here. This question could ask you, what is the molecularity of this reaction? And they're asking you how many molecules are involved. 1, 2. Bimolecular is what we would call that. How about this one? 1, 2. Bimolecular. Okay? Now, if you had only one, and it was breaking down, so A breaks down to make B plus C, something like that, that would be called unimolecular. And then if you had 3 or more in the reactants, that's called termolecular. And we just need to know what they're called. Okay? Unimolecular, bimolecular, and termolecular. Okay. Whew, what else we got? I'm ready to go home. The following results were obtained when the reaction presented above was studied at 25 degrees Celsius. Determine the order of the reaction with respect to A and B. All right, where is this problem? I think this is in my 0.006. No, where is this problem? Here we go. This is from one of my NMSI quizzes. We should have done this as a quiz, but that's okay. We only have so much time. All right, so let's look at A and B. So let's do A first. Between reactions 1 and 2, this is multiplied by how much? 0.75 divided by 0.25. Oh, it's multiplied by 3. Oh, remember how in the notes we always did it by 2? Well, they don't have to double it. They could triple it. So they tripled the concentration. So the concentration of A multiplied by 3, B is constant. And what's the rate do? What is, so this is A, right? 1.3 times 10 to the minus 3 divided by 3. Okay, so it multiplied by 3 if you plug in the numbers. So I get a tripling of A, we get a tripling of rate. That's first order, okay? So first order with respect, or let's just say with first order for A. And then let's look at B. Which 2 equations do I need to use for B? thinking in here I'm using 2 and 3. So between reactions 2 and 3. Okay, so this is tricky. So this is a table that's nasty. The concentration of A changes every single experiment. And so you have to look at the cumulative effect of both A and B and see how the rate changes. So let's erase this. We know that A is first order. Okay. Here we're going to double B. So B doubles. What does A do? A doubles. So when A and B both double, what does the rate do? Let's try 5.3 times 10 to the minus 3. Let's divide that by 1.3 times 10 to the minus 3. That's 4. So the rate quadruples. So rate quadruples. So 2 of those are from A, 2 of those from B. And so we can conclude that B is first order as well. First order for B. And I've been waiting for a problem like this where it's weird, right? Where you got some weird stuff going on. So first order for B. So let's write the rate law. Rate equals K, the rate constant, times A, times B. That's it. All right. I'm going to leave it there for a second. Is it weird that I feel like I need coffee? My coffee was bad today. It tastes like mud. It was so dark. It tastes like mud. I still liked it though. I like dark coffees, but sometimes it's like, ugh. Okay, that's what you get when you get some of the dark Starbucks coffees. All right, calculate the value of the rate constant. Okay, so I'm going to move this one up here. I'm going to delete this. And I changed something somewhere. Remember, I changed one of the numbers here. 51.2 hours. I can't do that. I'm going to have to copy the problem. Let's see what I can do. It's hard to have this on the screen and do it at the same time. Let's save this. All right, now I'm working with a modified version so that I have an original for you guys. So I don't have to, jack with that again. So, all right, so let's do. Okay. These are the same questions. Hold on, I've got. Let's close that. This looks like the same problem, but I have different questions here. Calculate the value of the rate constant. That's not what I just did. Open. The questions don't match. Okay, determine the order of the reaction with respect to A and B. Justify your answer. Write the rate law for B for the reaction. Okay, good. All right, now let's copy this and put this here. Okay, now let's do the second part. Let's do B. I just threw myself off. Okay, so calculate the value of the rate constant. So we're going to plug it in our rate law. Rate equals K times A times B. Let's plug in those values. I'm going to use experiment 1. Okay. So I'm going to do 4.3 times 10 to the minus 4 is equal to K times 0.25 times 0.75. So 0.25 times 0.75 is equal to K times 0.1875, dividing both sides by 0.1875. I get 4.3 times 10 to the minus 4 divided by, I get 0.0023 is our K. And the units for K, this overall order for this reaction is 2. It's 1 with A and 1 with B, so that's a total of 2. And so this will be M minus 1. And then this is minutes right here. So that's minutes minus 1. So that means 1 over molar times a minute. So either of those two units is fine for our K value. So that's our K value there. Wonderful. Okay. And I'm just going to delete this one and go to the next one. Determine the initial rate of change of A in experiment 3. The answers look different. I'm confused. So this is it's 1, 2, 2A plus B. I don't have this one in here. Give me 1 second. There we go. Woo. Okay. Just looking at the wrong part of this. Okay, we got our rate law. Units must be correct. Okay, so what we're going to do here is I'm going to move this down so we can just do one question at a time. And then I can write. I got some room here. I'm going to move this up though, a little bit. I don't even know if we're going to need that table. Just know that I'm pulling stuff from the table, okay? So the change in the concentration of A over the change in time is equal to minus 2 times 5.3 times 10 to the minus 3 and that is going to be equal to minus 1.06 times 10 to the minus 2. That's going to be molar minus 2 minute minus 1. Okay, so how did we get that? The reaction for this problem is two A plus B goes to C plus D. Isn't that what we had above? Yeah, 2A plus B goes to C plus D. Okay, so that's what we got. Okay, so that's our balance equation. And so we can multiply the concentration of A twice because there's 2 moles of it. So any change in that concentration will be multiplied by twice because there's 2 moles of it in the balance equation. So we're going to take 2 from the coefficient, multiply it by the rate from step 3, which is right here, 5.3 times 10 to the minus 3, and we get our rate. So this is the initial rate of change of A. That's the rate for the reaction, but we have 2 molecules of it. So we're going to do 2 times that rate. That's all we're doing. Okay? Okay. Let's look at what's the next one? This is going to be D. Okay, so let's look at D. D. It's not that. There we go, D. With that. Okay. Okay. So let's do D. Determine the initial rate of change of B. The initial rate of change of B in experiment 4. Okay, well, we can take the rate. We know the rate law. The rate law is equal to K times A times B. And we can plug in everything else except for the concentration of B. So we can plug in everything from 4. So that's 8 times 10 to the minus 3 is equal to K, which is 2.3 times 10 to the minus 2. And we wrote the K value as a decimal, but this is the same value in scientific notation. So that's K. And then A at this time is 1.75, according to the table, times B. And so we solve for B, and we get 2.0 molar. So that's just simple algebra. So you do this guy times this guy, get a number, divide this number by what you get. So you do 2.3 times 10 to the minus 2, multiply by 1.75, you get a number, and then divide 8 times 10 to the minus 3 divided by that number, and you get 2. All right, so we'll get 2 molar for B. Okay. All right, so that's D. The next one will be E. Oh, this one's cool. Identify which of the reaction mechanisms represented below is consistent with the rate law. So the rate law is so we want the slow step to have A times B. Can't be that one. That one has an intermediate in the slow step. Can't be that one. That one has an intermediate in the slow step. Oh, they all do. Okay, that's not a way to do it. Mechanism 2 is consistent. Rate proportional to MA. Okay, I think we got to do our equilibrium stuff here. So let's look at this one. All right, so we got 2B is an equilibrium with M. So the KEQ, the equilibrium constant, is equal to B squared. And then, wait, that's equal to concentration of M products divided by reactants squared. And then so we can solve this for M. So if I multiply both sides by B squared, I see that M is essentially and approximately equal to B squared. Because B squared is multiplied by KEQ, and KEQ is a constant. This is a constant. And so it is proportional to it. You just multiply B squared by some value, and then you get M. But as the reaction proceeds and as things change, the concentration of B will change, but KEQ is not changing. Okay? And so M is approximately equal to B squared. And so let's see, rate proportional to m times a. M is proportional to b. So what I have here, it says mechanism 2 is correct. B squared plus a. Mechanism 2 is consistent. Rate proportional to m times a. And m is proportional to b. I got b squared. I don't know where I got b squared. Where do they get the b? Verbal discussion accepted for second point. Mechanism would be consistent with rate law. Okay, I'll look at this one. I'm getting b squared. Somehow they got b. And so they're saying that it's b. So m is proportional to b. And so then the rate law becomes rate equals a times b for that second step right there, for that slow step. So if you replace m with b, then it's a plus b, and the rate law will be a times b. Man, this one's a little tricky. And it's got some equilibrium stuff on it. But that would be our mechanism. Okay, and that's at the end of it. Okay, let's do 16. I'm just going to leave these on here, and I'll show these to you guys. We'll have to do these another day. Or maybe during class, we'll do them after the video. Okay? But I did up to 15. All right, thanks, guys. Hope this was helpful.